Hello everyone, and welcome to another math tutorial on circles. Our last video we discussed the angle relationships in circles, and in this video we're going to talk about some segment relationships that we might find in circles. Well, let's take a look. Our first theorem looks quite similar to one that we talked about in the last video, at least as far as the picture setup goes. We've got a circle with two chords that intersect on the inside of the circle. The difference here is we're not interested in angle and arc measurement relationships, but we're interested in segment relationships. So this theorem says if two chords intersect inside the circle, then the product of the segments of one chord equals the product of the segments of the other chord. So let's find those pieces in the diagram here, just and kind of color code them to kind of highlight what we're looking at. We've got these two pieces, two segments on segment AB. So we've got EA times EB. And the product of those two segments is going to be equal to the product of the two segments of the other chord. So you see those pieces here. All right, let's see that this first theorem in an example problem. Directions in this first problem are simply to solve for x. We see this again, familiar setup. We've got a couple of chords intersecting inside the circle. I've got these two segment pieces on one chord, and then these two segment pieces on the other chord. And what I'm going to do is find the product along each chord. So I'm going to take 10 times 7x. Okay, that's this chord. I'm going to equal that to 15 times 5x minus 2. All right, so there's our setup. If we go off of that theorem, now we just need to solve this equation. 10 times 7, 70x equals, we'll distribute the 15. So 15 times 5 is 75x. And then we'll have minus 15 times 2 is 30. And take the 75x and subtract it over to this side. So I've got negative 5x equals negative 30. And if I divide by negative 5, we get x equals 6. This next theorem is called segments of secants theorem. Instead of just presenting you with a wall of text that is the theorem, I thought we'd just look at a picture. I've got a formula here and kind of a description of the formula. But let's kind of find the pieces in this diagram as it relates to this equation down here. So the way this works, we've got two secant segments, and the secant line itself, or segment itself, EB, is divided into a couple smaller pieces here. And so here's how this is going to work. You start with the external segment. So I'm going to start with EA right here. And we see that right here. And then I'm going to multiply that by the length of the entire segment, EB. You see that right here. Okay, so it is the outside or external piece, and we're going to multiply by the whole thing. Okay, that's one side. And we're going to do the exact same thing to the other secant. We're going to take the external part, and then we're going to multiply that times the whole thing. Okay, so that's how the equation works. We never use just the interior piece. Okay, it's not going to be used. It's outside times all of it equal to the outside times all of it. All right, let's see that in an example problem. All right, here we go. Another problem where we're asked to find the value of x. Here we've got these two secant segments. So I begin this by, and it doesn't matter which segment you take, but I'm going to begin this on the top segment. I'm going to take the outside piece, which has a length of 9, and I'm going to multiply it by the length of the entire piece. Now that's confusing sometimes. We want to take 9 times 11, and that's not going to be correct because the entire piece does not measure 11. If you add these pieces together, 9 and 11 makes the entire length 20. And that's what we're going to multiply by. So the outside piece times the entire thing. I'm going to do the same thing on the other secant. I want the outside length, which is 10. I'm going to multiply by the length of the entire thing. And the entire thing, just like up here, 9 plus 11 gave 20. I'm going to do 10 plus x. Only I can't put those together any more than that. So there's the beginning. Now we can start to solve this equation. 9 times 20 is 180 equals, and we'll distribute the 10 there. We have 100 plus 10x. And take our 100 and subtract it to the left-hand side, giving us 80 equals 10x. And divide both sides by 10, we get x equals 8. All right, we're going to close this video with one more theorem and then one more example problem to support this theorem. This one is segments of secants and tangents theorem. So here we've got another secant line like we had in the last theorem and example, but this time we also have a tangent segment. And so how we deal with that is very similar, but it looks maybe a little bit different down here. First, let me look at just the secant segments. So let's look at the bottom first. We've got this outer piece, EC. We're doing that again. And then we're going to use the whole thing, ED. Okay, so there's no difference at all to how we do that. From the previous theorem. It's the external piece times the entire segment. Now when we go to the tangent segment, we're actually going to do the same thing. We're going to take the external part, which is EA. Let me write that out. We're going to take the external part, EA, and then we're going to multiply that by the length of the entire thing, which just so happens to be EA again. So the formula, you can see it's written a little bit differently. It's just written as EA squared, as that would be a way to re-express EA times EA. So taking the tangent segment squared times, and then on the secant, the external times the entire thing. Okay, time for our final example problem. I'm going to begin this one on the top secant segment. I'm going to take the outside piece, which is 5. I'm going to multiply by that by the length of the entire thing, which is 5 and x put together, 5 plus x. And I'm going to equal that to, now here I just have a tangent piece, so I'm going to take the outside piece times the whole thing, which just ends up being 7 times 7, or as the formula wrote on the other slide, 7 squared. But you can't think of it just like this. You can think of it as outside times whole thing to get 7 times 7. All right, let's solve this out now. We have 25 plus 5x equals 49. We are going to subtract 25 from both sides, giving us 5x equals 24. If we divide both sides by 5, we get x equals 24 fifths. It doesn't reduce, so you can just leave it as 24 fifths. If you want to re-express that as a mixed fraction or as a decimal, that's up to you, but I'm happy with 24 fifths. Okay, as always, if you have any questions, please drop them below in the comment section and I will get to answering them as soon as I can. If you found the content in this video helpful, please give it a thumbs up to help out the channel, and I'll see you in the next video.